Okay, so today we are going to discuss about operational amplifier, that is better known as op amp. This is the most important building block in any type of analog circuit design. Okay, today we will give stress on the internal structure of op amp, I mean two-stage op amp, and we will discuss about the small signal gain and frequency compensation, about all this stuff. And tomorrow we will go for the real design. Okay, we will discuss about the design rules tomorrow. So let's start with today's discussion. This is the basic symbolic representation of op amp. You all know about this. This is big triangle representation. You all know. For an ideal op amp, the following characteristics, op amp should have the following characteristics. First, that infinite input impedance. That means no current should enter through the input terminal. No current. Ideally, it should have, but obviously we can't have infinite input impedance. Second one, as you can see from the voltage gain formula, that V out is equal to A into V plus minus V minus. So here from actually we just do what, V plus minus V minus, we just we force to make these equal, make these two equal, so that the infinite open loop gain becomes infinity. Obviously these also we can't achieve, more or less 10 to the power 5 or 10 to the power 6 we can achieve open loop voltage gain. Third one is that the V minus voltage, as this is forced to be equal with the V plus, and these should remain constant all over the time. This is termed as virtual ground in time of small signal analysis. Okay, an op amp works in between two voltage supply, that is Vs plus and Vs minus. These are called rails. Vs minus is often taken to be ground. Actually this is not a actual ground, I mean Vs minus is basically a reference. So for the sake of simplicity we can take it as a ground. Okay, for the sake of simplicity. So these are all the ideal op amp characteristics, but we should discuss about the real op amp. Now the differential voltage gain, as we have seen in the earlier slide, that it should have infinite gain. Second one, that input impedance should be very high and output impedance should be very low, but these two characteristics are strictly for operational voltage amplifier. Okay, so there are four types of amplifier: voltage to voltage, voltage to current, current to voltage, and current to current. So if I write that this is V to I, I to V, V to V, and I to I. So for this V to V, input impedance, input Z should be Zi, Zi should be high and Z out should be low. I am telling you a thumb rule that in the input side, if you want to sense a voltage, then you have to give a high input impedance, and if you want to sense current, you have to give a low input impedance, and in the output side the reverse should be done. Actually to sense the voltage you have to give a low impedance, and to sense current you have to give a high impedance. So I think now you can fill up the table. I mean for the whole I to I, that Zi should be low and Z output should be high, something like this. Okay, so these are the basic characteristics. Now from now on when I say that voltage gain, we will strictly think about that this is a voltage, I mean gain means here voltage gain from now onwards. This is the basic structure of a common source NMOS amplifier with active load ID. You all know that the small signal gain of this type of structure is simply AV is equal to minus GM into R naught. Okay, R naught means basically the drain to source resistance, that is basically equal to 1 by GDS, that is basically equal to 1 by lambda IDS. So these are the relationships. Any one of that, I mean any of these can be used whenever it is wanted. Something R0 is this, R0 is this one, that can be 1 by GDS, that is RTS, that is 1 by lambda IDS. Okay, And you all know about the DFAM schematic. Just in the previous class you have done this n channel input differential amplifier. The small signal gain of this type of amplifier is basically minus GM1 into R02 parallel R04. GM1 means the GM of the M1 transistor, and R02 parallel R04 means you can have this simply from the small signal model. So can you tell me that by using this model can we achieve a high voltage gain? Can any one of you tell me that a very high voltage gain can we achieve from by this configuration? No. I am giving you the answer no. But what is the limitations of this type of configuration? DFAM. See, when we are talking about voltage gain means from the formula it is minus GM1 R0 parallel R02 parallel R04. Okay. Now first we consider GM. GM is basically nothing but proportional to ID and obviously proportional to W by L, and R0 is proportional to equal to 1 by lambda ID, as I have told just right now. So overall AV becomes proportional to root over W by L, root over aspect ratio, and inversely proportional with lambda and root ID. Okay. So if we want to increase voltage gain, we can have three options. First one is that we can decrease ID, that is primarily I am rejecting that because we can't afford that to decrease ID. Then the other two options are increase of W by L or decrease of lambda. Now if we want to increase W by L, the aspect ratio, W by L means of what stage, that is for the GM stage W by L means input M1 transistor. If we want to increase W by L, then we have to increase W, and again if we want to decrease lambda, lambda means for what transistor, for that M2 and M4 lambda R02 parallel R04. So lambda is associated with those two transistors, and in the laboratory you have already seen that lambda is inversely proportional with L, length. So if you want to decrease lambda, then we have to increase length. So both of these, that means increase of aspect ratio or decrease of lambda, both of these leads to increase in chip area. Okay, either increase of W of the M1 or increase the length of M2 or M4. So both of these tends to increase the chip area. This is obviously not a desirable effect. So what is the option to increase voltage gain? Here comes the necessity of a two-stage opamp. This is basically termed as opamp, and the previous one is termed as DFAM, but DFAM is obviously a special case of opamp which has only got a single stage. Okay. So this is a two-stage opamp schematic. We will consider right now, we will consider about the portion in the green rectangle, and the portion in the red rectangle we will discuss it about later. That is the basically compensation portion. I will discuss it about these later. So first, here is the two-stage opamp. Okay, from the schematic you can easily calculate the gain of the first stage. What is the first stage gain? First stage gain means that minus GM1 into R02 parallel R04. And what is the second stage gain? Second stage means this portion. Okay, second stage means that M1, these M6, this portion M6 and M7. So this is connected as like this. Anyway, so GM of what? Okay, but is this visible? Yeah. So what is the voltage gain of second stage? Second stage voltage gain should be minus GM6 whole into R06 parallel R07, because the input of the second stage is basically the gate of the M6 transistor. So GM should be associated with the M6 transistor. So minus GM6 whole into R06 parallel R07, similar to the first one stage. So overall gain should be like this: GM1 into GM6 whole into R06 parallel R07 whole into R naught 2 parallel R naught 4. Clear? So clearly you can see that we have already increased the voltage gain without increasing the length of any, I mean area of the chip, not area, I mean individual transistor length or width. Without increasing that, we have already increased the gain. As we have introduced a new stage, we have introduced a new pole. These are the two new poles. These are the poles in the transfer gain. P1 is associated with the basically minus 1 by RC is the output resistance into load capacitance. This is basically gives you the pole. So here output resistance for the first pole, any one of the pole, is that these are not 6 parallel are not 7, that is the, I'm talking about the point A, okay, in this schematic point A. So here this is a C load. C load means I have attached a C load at the output of the second stage. So basically what would be the pole associated with these, with the second stage? Minus 1 by C load into R naught 6 parallel R naught 7. Clear? And what about the second pole? I mean the other pole? Other pole should be here the associated capacitance of the first stage, multiplied by R naught 2 parallel R naught 4. As you can see from here, capacitance of the first stage associated with multiplied by R naught 2 parallel R naught 4. So these are the two poles. This is a two pole system. Diffamp was a single pole system because it has got only one stage. Now we have introduced a new stage and we have introduced a new pole. This is a two pole system. Here is the plot, Bode plot. So gain and phase, is it visible to all of you? Yeah. So here comes a new term, that is phase margin. Do you know what exactly phase margin is? Phase margin is basically the difference between the phase shift of the op amp when it is crossing that at gain crossover frequency. Gain crossover frequency means at the frequency where the gain plot crosses the 0 dB axis. Okay. So if you go with the for this vertical line, so you will have that the total phase shift is minus 217 degree, and the difference between these with the minus 80 degree, minus 180 degree will give you a phase shift, phase margin. So here phase margin becomes how much? Phase margin becomes minus 217 minus 18, sorry, minus of minus 180 degree, difference between the two. So it gives you nearly 37 degree, minus 37 degree. This is an unstable op amp because we cannot afford a negative phase margin. Okay. So we need to make this stable. How we can do that? This is basically the simulated result of a unity gain buffer without any frequency compensation. So you can see that the output varies, I mean increases the oscillations as the time goes on. So this is basically a unstable op amp, as you can see from the plot. Okay. Here is the basic term we have. I have just told you the difference between the actual phase shift as mod AV tends to 0 dB and minus 180 degree, that gives you the phase margin. For a good, I mean for a stable amplifier, you should have a positive phase margin, and for a good design it should have a value between 45 degree to 70 degree. We can take 60 degree as a good value. Okay. So this is a problem. I am just going about the stability for that problem. So solving that, but before that some of these, that closed loop transfer gain something like this, 1 plus a beta, that means the denominator. If the denominator becomes 0, then obviously the system will be oscillatory. That is also an unstable system. Okay. So we need to do what? We need to employ a frequency compensation network. Okay. Frequency compensation network basically does what? In the previous plot we have seen that the main problem is that the two poles are very near to each other. In the op amp stage, the two stage op amp, the two poles are very near to each other. So what is the problem? Say here is P1, that is P2. So here a drop and something like this. Okay. Now what about the phase? Something sorry, this was something like this. So you can see that at 0 dB, this is 0 dB, at 0 dB this is a negative phase margin. Okay, that is basically the instability. So what we need to do for the frequency compensation, we try to split the poles. We try to split the poles. Split the poles means from this plot, we need to we just try to move P1 in this direction and move P2 in this direction, so that this phase margin becomes positive. How it can become positive? Something like this. The change in gain plot will be something, say we place P1 here and P2 much far away, I mean not far away, but P2 we place P2 much larger at a frequency much larger than unity gain bandwidth UGB. That means what is the unity gain bandwidth? This portion. Okay, so we place P2 somewhere here. So what is the plot? New gain plot will be something like this, and then a fall. So this is our UGB, new UGB. Okay, and what about the phase shift? Phase shift means for this pole, the phase will starts to decrease at about omega by 10. At the frequency starts to decrease at about a frequency omega by 10. So something like this. Still for these also it will start to decrease on omega by 10, but as you can see from here that at this frequency we have got a phase margin of positive value. Basically as you can see here that we have moved the poles. Now the new phase shift is near about minus 135 degree. So what about the phase margin? Difference between minus 135 degree and minus 180 degree, that is basically plus 45 degree. So this is a stable op amp. Got it? But splitting of pole is basically a proposal. I have given you a proposal, but how to employ that in a real circuit? How to do that? How to realize that thing? Realize that thing, we can realize it by using a capacitor, that is called compensation capacitor. Okay, as you can see, this is the red area, that is basically for the compensation portion. I am not talking about the resistance right now, I am just talking about this capacitor. So we have introduced a new capacitor, that is called compensation capacitor. Okay, this will increase the phase shift by splitting the poles, as you can see here. So by introduction of see here that in the small signal analysis, CC is basically here, and you all know Miller's theorem. So CC basically something, this is C1 and here is that C, and if we can just here this and this, so this C can be effectively divided into two parts, that is C1 effective or and something like this C2 effective, applying this portion C2 effective, applying Miller's theorem. So and if you just imply the simple node equations, you will get this oh just a minute. So what is the value of that C1 effective and C2 effective? We just need to know the voltage gain. As you know that the formula of that Z1 is equal to Z by 1 minus AV, and we have calculated that A is basically minus GM to R2, and from that equation we can easily calculate effective C1 and effective C2. Okay, so what is the role of that CC, compensation capacitor? This just split up the poles. Got it? Obviously the two poles will have a new position. Splitting up the poles means this will have a new position. P1 has moved towards the left and P2 has moved towards right. Okay, so what are the new two positions? You can easily solve the KCL equations for the V6 node and output node, and where from you can get three things, that the voltage gain and corresponding P1 and P2 with some easy calculation, obviously tedious calculation, but easy. So you can see that P1 is a function of Cc, compensation capacitor, and P2 is also a function of compensation capacitor. So we have considered and you have seen the plot right now here. So we have increased the phase margin. System has now become stable, but there is one drawback. I mean, introduction of Cc tends to incorporate something, some new drawback. What is that drawback? That is a feed forward action. Feed forward action actually introduces a new zero in the system. Okay, that zero is equal to basically plus Gm2 by Cc. Plus Gm2 means that is a right half plane zero. Okay, that right half plane zero obviously increases the gain but affects the phase again. So our primary issue to introduce Cc was to improve phase margin, but again for the feed forward action we are left with the same situation where we were. So how to remove that? We want to retain the advantageous part of Cc. That means we want to increase the phase shift as it does, but we want to remove that disadvantageous part of Cc. That means that zero. Feed forward action introduces a new zero. We want to reduce the effect of this new zero. We want to reduce that. For that, we introduce a new resistance here in series with that compensation capacitor. Okay, this resistance is called nulling resistor. Nulling resistor does what? The new zero comes like this, Gm2 by Cc, and this is a basic thing, and the voltage gain comes like this. As you can see from here, that new zero comes from here. You have seen that the new zero comes like Gm2 by Cc into 1 by 1 minus Gm2 Rz. Okay, and the overall voltage gain comes like this. So applying Rz, what we can do? We can place zero. We can place that zero, that right half plane zero, anywhere in the plot we want, depending upon the value of Rz. Okay, we can clearly place that zero anywhere in the plot by varying the value of Rz, and obviously we want to put that zero at some frequency which is far away from the unity gain bandwidth, which does not at all affect the phase plot at the gain crossover frequency. That is one option. And you can see that in the denominator also there has become a new pole, because this is a third degree equation, so it has become a new pole. So another option you can do, by choosing the value of Rz, you can place that zero in strategically in such a position that this third pole and that zero coincide. Sorry. So you can place that zero and third pole at such a situation, strategically you can place them together, I mean coincide. So what will that do? That will obviously individually, none of them individually can affect the circuit. Both of them will reduce their own effect. So Rz, by varying the value of Rz, oh just a minute, B, C, D, these coefficients also are a function of Rz, but Rz affects very negligibly for that value. So if we want to change the value of that position of that zero, it does not at all affect the position of P1 and P2. So right now where are we? We have retained the advantageous part of Cc. That means that phase margin that is not affected by the new introduction of Rz. Feed forward action has been removed by introducing that Rz, that nulling resistor. Okay, and introduction of Rz gives a new zero, that right half plane zero, and we have removed that part also. Rz, introduction of Cc has gives rise to a new zero. we have removed that part by introducing a new nulling resistor, that is RZ. Okay. So RZ can act as a two-way, that we can place the 0 at some frequency which is far away from the unity gain bandwidth, that it does not affect the phase margin, or else we can strategically place the 0 and the third pole at some position, at same position, so that none of them can individually affect the circuit. Okay. So by the compensation, now we can see that the red area, I mean the portion between the portion in this red area, we have seen that we have introduced a new resistance, compensation resistance, that is called nulling resistance, and a compensation capacitor. Okay. So both of these make something, this is called frequency compensation, both of these. So what is the summary of this compensation? We were just instability of, we were in such a position that instability of op amp was coming from that two pole system, and the pole were very near to each other. We have split up the poles by introduction of compensation capacitor, split up the poles, but this gives rise to a new problem, that is introduction of a 0, right half plane 0. We have reduced that part by introducing a nulling resistor, and we have retained the phase shift as good as it were at the time before after the compensation capacitor were introduced. Okay. So this is basically the structure of and after introduction of CC and by doing the frequency compensation, we have got this plot. You can see clearly, I have told you that the phase margin in this case is near about 45 degree, which is good enough, which is good enough. Okay. So, and this is basically the step response of a, I mean not the step response, basically the unity gain buffer characteristics. In the input we have just given a step, that red curve, you can see that the red curve, and the blue curve is the output. It just follows the input, obviously it is a voltage follower. So the input, the output follows the input, and after compensation it gives a very good following characteristics, because in the previously we have shown that the oscillations were there, but after introducing that compensation capacitor and that nulling resistor, we have removed that oscillations, and it has given a stable op amp, as you can see there. Now obviously frequency compensation must be considered in the op amp design. Got it? This is the step response. This is the step response of an op amp. This is the basic structure. So we can write the basic node equations at this position. I mean current at the output means what? This node minus this node. What is this node? Voltage of this node. This node. It's not getting this are behind at the output of that amplifier. What is the voltage at that position? That is basically A into V in minus, V in is the voltage at the positive terminal, and negative terminal means V out. This is acting as a voltage divider, this R1, R2, and at the topmost position there is V out. So in between the position, the node between the R1 and R2 is acting as a voltage divider. So the voltage at the negative terminal is what? V out whole into R2 divided by R1 plus R2. Voltage at the negative terminal, V in minus V out into R2 divided by R1 plus R2. Okay, this is the voltage at the just output at the op amp, and what is the this minus V out divided by R out will give you the current flowing through this R out. Okay, and what is the value of these? What is the value of that current? I mean equal to what? Equal to basically V out divided by the equivalent resistance between the parallel combination of R1 plus R2 and CLS. In S domain what we get is that R1 plus R2 parallel 1 by CLS. Clear? So where from we get the voltage gain? As you can see from here, that that is the voltage gain. This is the voltage gain. So here the this is in the form of something like k divided by s plus a. So you all know Laplace. This is in the Laplace domain, I mean S domain. So this is in Laplace. So what would be the output voltage in T domain? I have given a step response. I have given a step response. So V in should be 1 by S. V in S. V in S is basically 1 by nothing but 1 by S. Okay. So if you multiply these, that means V out S is in the form of something like K by S plus A into 1 by S. In the form of this, by partial fraction, what we can see that this is in the form of something like this. Got it? So what is the final form? If you do inverse Laplace, you will get something like this, some k3 into 1 minus e to the power minus t by, I mean at, okay, at. Clear? This is the V out. You can correlate with this form, and that exponential e to the power minus t by that whole portion we can term it as tau. This is in the standard form 1 minus e to the power t by tau, that is the time constant. So you all know, I mean you know all the factors CL, R out, open loop gain A and R2, all these things are known to us. So easily we can calculate tau. So what should be the settling time? Can you tell me? How can we determine the settling time? What is the final value? Final value of this output voltage? Just put t is equal to infinity. Steady state value will be achieved, and the at t equals to infinity, the output value just becomes V naught into A divided by 1 plus A into R2 by R1 plus R2, because e to the power that portion just gets a 0 value. Okay, so we can write that. V out is equal to Vf into 1 minus e to the power t by tau in the form of like this. We have replaced that portion. So settling time means what? Settling time means what? Not 90%, actually it enters the tolerance band. Tolerance band means near about 2 to 5% of the final value of the steady state value of the voltage. But in real design, this is a theoretical value 2 to 5%, but in real design it should be within the value of 0.5 to 1%, maximum 0.5 to 1% in real design. So whatever be the value of that thing, that tolerance band, we can put the value over here. That means V out, what should be the value of settling time? That means if we just right now we are considering about 2% value. So these portions should be 0.98 because it has already achieved the 98% of the output. That will give you t. So 1 minus t e to the power exponential e to the power minus t by tau is equal to 0.8, and from there, and you know tau. So from there you can easily calculate t. So that will give you settling time. Okay, and this response is called linear settling. Nothing for that, only settling time calculation. Anyway, next thing is this. What is a slew rate? Slew rate means basically the change of output voltage with respect to time. Okay, change of output voltage means say we have given a step like this, and output in real system, obviously the output cannot actually track the input immediately. It should have some ramp action, something like this. It should have a slope. This slope is called the slew rate, the change of V out with respect to t. Okay, so how to calculate the slew rate of an op amp? Means the change of voltage, change of output voltage with respect to time. Basically output voltage gets changed with just see here. Okay, I am just sorry, here I am just considering among the only resistance, compensation capacitor, compensation capacitor, just consider that thing. Now this portion, this is okay. So this is the V. and this is, anyway, here this is the V out. Okay, V out obviously will depend upon the variation. I am just right now I am neglecting this part, CL is not there. So V out obviously will depend upon the variation of I mean depend upon CC, compensation capacitor, and what will be the value of dV out dt. I mean V out is basically the charge stored at this capacitor divided by the value of this Q is equal to CV. From the capacitor relation it is Q is equal to CV. So what is V? Q by C. Q means the current flowing through this capacitor into time. So current flowing through that capacitor into time divided by the value of that capacitor. Okay. Then now what is that current value? If we just need to draw the whole circuit. So here is the thing. Sorry, this is V in plus, this is V in minus. Here this is this is M1, this is M2, this is M3, this is M4. Something like this. This comes there. So here is the V out and this is the CC. Okay, this is the whole structure. This is VB, VBus. So this is the whole structure. Say when we have just given a step input at this terminal V in plus. Initially, this is off. That M2 is off, M4 is off, and M3, M1, 4 of them are off. Okay. Now if we just have given a high input at this M1 M2 gate of that M2 gets on. Okay, here is a path, a high current flow through this path because at high frequency this CC gets shorted at high frequency. Okay, so this at this path a high current flow through this circuit. This is always on. There is this M6, a high current flow through this path. Okay, say this high current is termed as ISS. So what is the value of that voltage across these CC? V out means ISS into T divided by CC. Okay, so what is the slew rate? Slew rate means dV out dt, that is basically ISS divided by ECC. This also gives you an important parameter, that means the maximum current driving capability of the circuit. CC determines some other thing also, slew rate determines some other thing also, that is the maximum current driving capability, because this is the maximum current. Okay, so maximum current driving capability means slew rate is defined as ISS by CC. So CC helps you determine that thing also. So in the determination of slew rate, there is a portion of CC that is also a function of compensation capacitor. So compensation capacitor acts in a two way. The most important two thing is that one thing is phase margin, the stability of the opamp comes with the good phase margin, which actually is given by the introduction of CC, that compensation capacitor, as we have already discussed that portion. And now we are seeing that the slew rate is given by the CC also. So the determination of the value of CC is a very critical issue during the design of an op-amp. First and foremost thing, you have to determine the value of this CC very accurately. Okay, so this is the portion here. the slew rate has become like this. Now we are giving you, I am just giving you a simple overall idea of cascading of op-amp. Cascading of op-amp means, as you can see, if for both of the structure, I am talking about both of the structure. This is a single-ended structure and this is the differential output structure. In both of the, in a single stage DFAM, what is the small signal voltage gain? AV is equal to minus GM into R naught. Sorry, R naught N parallel R naught P. That was M2 and M4 for that too. Here, this R naught N due to the introduction of these stack transistors, I mean transistor at the uppermost portion, this R naught is changed to something like this. R naught N is multiplied by GMN into R naught N, and this R naught P changed to something like this. So, what is the value of new voltage gain? New voltage gain should be something like this. GMN means the input stage of the that first GM that comes in the small signal voltage gain, that is obviously associated with the first stage transistor, and that is in NMOS configuration, that is a NMOS. So, this is basically GMN multiplied by R naught N square GMN parallel R naught P square GMP. Clear? So, we have increased the voltage gain, the prime issue to increase the voltage gain, we have increased that voltage gain considerably. Okay. And if you now go on increasing the number of transistors in the stack, I mean if you go on increasing M6, M8 and then M10, M12, you will go on increasing the voltage gain. Okay, this is called gain boosting. Basically this is called gain boosting. But what is the disadvantage of this type of configuration? Because I am telling you, in real design we do not use these often, though we have a considerable amount of high voltage gain, and if we just go on increasing the stack transistors, then we will have higher and higher voltage gain, but still we do not use in a real design, do not use often. Why? What is the basic limitation of this circuit? Basically in a two stage op-amp, in a DFAM, single stage DFAM, say the prime advantage of this portion is we have increased the voltage without increasing the second stage. Okay. So, what is the disadvantage of this type of configuration? In the DFAM, we have already discussed that V out, maximum V out is limited by this VDD minus VD sat of this portion. Okay. But in case of cascading, in case of cascade op-amp, what is the maximum value of V out? V out is limited by VDD minus twice of VSD in these of two transistors. If we go on increasing the number of transistors in the stack, then obviously this V out will be limited by the higher value of that. So, this is basically we are having with a reduced voltage swing. Obviously, this is not a desirable one. Okay, voltage amplifier should not give you a reduced voltage swing. So, unless you are left with only option that you want to have a very high voltage gain, we should not use a gain boosting op-amp in this cascade amplifier. Okay. And one last thing, one more thing, that we have already discussed about the two stage op-amp, I mean that DFAM using that NMOS transistor. Input stage is NMOS. What is the drawback of that NMOS transistor is that, see, the operation of these transistor, this DFAM, we are considering just only for these. So, operation of this DFAM is basically limited, that the lower value of V in should be such that it is in the saturation, all the transistors are in saturation region. Okay. So, what should be the minimum value of these VTN plus the value of this VD sat, okay. So, VD sat is near about 0.2 for an NMOS, and VTN is something like 0.4 or 0.5. So adding them up, we are getting that 0.7. So a 0.8 volt is good enough to make all the transistors operate in a saturation region. Okay, so V in should be greater than 0.8 volt, and what would be the higher value? As I have just told you, that would be VDD minus VDS sat for the PMOS transistor, and for the PMOS transistor, that VDS sat is something like 0.1 to 0.2 volt. That is becoming that the higher value of these maximum V in is 1.6 or 1.7 volt, say 1.6 volt. So the range of operation for this NMOS circuit is becoming something like this volt, 0.8 to 1.6 volt. Now if we want to sense a very low voltage, then what to do? I mean like 0.2 or 0.3 volt, what to do? For that reason, we can introduce a new structure, that is a PMOS diffamp. Okay, PMOS diffamp is something like this. This portion is replaced by a new opamp, something these, sorry, V in minus, V in plus. So this is the basic structure for an, we are giving the input to these PMOS transistors. Instead of giving that those input in the M1 and M2, we are giving the input to these terminals, M3 and M4. Okay, so what is the advantage of this thing? Advantage of this thing is basically you can see that the higher range of V in should be something VDD minus VTP minus VDS sat. So that will give you something 1.8 minus for the minus 0.5, and for VTN VDS sat it should be something like this. So it is becoming 1.1, we are taking it as 1 volt, and the lower range of this circuit we get 0.1 volt. So the range of operation for PMOS diffamp is 0.1 to 1 volt, 0.1 volt to 1 volt. Okay. So in this case also, if we want to sense a voltage near about 1.2 to 1.3, we can do that. So option is that we can use both of these structure, NMOS and PMOS structure, both of these structure together, that is called folded cascode. So this is not in the scope of this discussion, so we are leaving that. But the thing is that basic thing is that in NMOS transistor, NMOS diffamp, there is a basic limitation that the lower range of operation is getting limited by 0.8 volt or something like that. So below that value we can't sense that, we are below the value of that voltage we can't sense that. So we need to use in that case a PMOS diffamp, and if we use both of them together we can have a long range from 0.1 to 1.6 volt, long enough to sense any voltage between 0 to VDD. Got it? This is the overall view of any type of op amp. Now we should discuss about one problem, one simple problem, very simple problem. Just consider a 2 poles 1 0 system, that is basically a op amp, 2 stage op amp. If 0 is forced to be 10 times higher than GB, then GB means unit gain bandwidth, then the second pole has to be placed at what position for phase margin to be 60 degree? What should be the position of the second pole? first write down the gain expression using just 2 poles for a 2 poles and 1 0 system. You can try it. This is basically the gain formula, isn't it, for a 1 pole for a 1 0 and 2 pole system. So just equate the phase margin with the angle of these. So what is the phase shift? Okay, I am just writing phase margin. Phase margin formula is basically something like this: plus minus 180 degree plus angle contributed by 0 zeros minus angle contributed by poles. So here, and what to choose in between plus or minus 180 degree, this is basically phase shift. This portion is basically phase shift. So depending upon the value of phase shift, we just need to choose plus or minus 180 degree, whatever be the value of I mean, to make this phase margin positive. Okay, we need to choose that. Okay, so here in this case, this is 180 degree plus tan inverse of minus omega by z1. Why this minus? Because this is a right half plane 0, as you can see that 1 minus is by z1. And what is omega? Omega, I am taking that omega is the unity gain bandwidth frequency, I mean unity gain bandwidth, I am taking that, minus tan inverse omega by p1 minus tan inverse omega by p2, isn't it? So these minus will comes outside, that means phase margin should be 180 degree minus tan inverse omega by z1 minus tan inverse omega by p1 minus tan inverse omega by p2. We know omega by z1 means what? 0.1, because z1 is 10 times larger than omega. I have told that in this problem, in this given problem, z1 is 10 times larger than omega. So this portion is 0.1. Omega by P1, tan inverse omega by P1, yeah, that is 90 degree. Okay, omega by P1 is a very large value because P1 is the at the lower frequency range. So this gives you a 90 degree phase shift. So now you can easily calculate, and PM is 60 degree. Okay, so tan inverse omega by P2 should be 90 degree minus, that means 30 degree minus tan inverse 0.1, that it gives you a value of something 24.3 degree. Okay, so here from omega by P2 is equal to tan 24 degree, sorry, tan 24.3 degree, and where from we can get that P2 is obviously larger than GB, 2.2, 2 times larger than GB. So what I told you in that discussion, that P2 should be placed somewhere far away from the gain bandwidth. So that is basically you should place it near about larger than 2.2 times gain bandwidth, sorry, gain frequency in EGB, unity gain bandwidth, 2.2 times larger. Okay, you can try it for another design also, that is phase margin for 45 degree or 70 degree, whatever be the case. This is a standard case. 60 degree is for a very good design. Okay, this is the whole scenario. This is also the theoretical part, the real design part, and how to go with for that calculation of CC, and for the iteration, I mean calculation of that CC, how that affects the other parameters. We will discuss about those things tomorrow, the real design issue. Okay, so should we call it a day? Any problem? Any query?